Okay, so we're done talking about sets, and I want to start talking about functions. So the next several lectures are going to be about functions, and then when we've finished talking about functions, then we'll give an application in terms of personal finance, right? So how functions appear in personal finance. Now, why are we going to talk about functions? Well, because functions, sets are sort of the building blocks of functions, right? And functions are the building blocks of a lot of other stuff that we do in math. So a function is basically just a rule that assigns each element in one set, called the domain, to exactly one element in another set, called the range. Okay, so it's a map that takes you from one set to another set, right? That's what a function does, right? And one important word here in this definition is the word exactly, right? So a function has to assign each domain element, which we sometimes call inputs. So it has to assign each input to exactly one range element, which we sometimes call images or outputs, right? So we have to. So it has to take one. It has to take each input and map it to exactly one output, right? So it can't be mapped to two separate outputs or multiple separate outputs, and it also can't be mapped to no output, right? It has to be mapped to exactly one output. So here are some pictures to kind of show you what a function is, okay, and what it's not. So if this is your domain and this is your range, and maybe you have your domain is made up of the letters A, B, C, D, and your range is made up of the symbols square, circle, star, and oh goodness, what else? Like, why can't I think of any shapes? I guess we could do a diamond, right? And maybe your function maps A to the circle, and it maps B to the square, and it maps C to the star, and D to the diamond, right? That would be a function, right? That's a function, because each domain element is getting mapped somewhere, and it's only getting mapped to one place, right? So this is a function. Okay, here's another function. So let's say, again, that your domain is made up of the letters A, B, C, and D, right? So that's your domain. And that your range, let's say your range this time is only made up of the shapes square and circle, right? And you map A to square, and B to square, and C to square, and D to circle. Okay, this is still a function, right? It may bother you that like 3 of our domain elements are getting mapped to the same range element, but that's perfectly fine, right? Because you can have that situation. That's not a problem. It's just that we can't have a domain element going more than one place, right? So A is getting mapped to the square and only to the square. B is getting mapped to the square and only the square. C is getting mapped to the square and only to the square. And D is getting mapped to the circle and only the circle. Okay, so what we can't have would be a situation like this, where you have your domain is made up of like ABC, and let's say that your range is made up of square, circle, star, and diamond, like it was before. Okay? If you had A going to the square, and B going to the circle, and then C going to both the star and the diamond, that's not a function. It's not a function. Okay? So that's not a function. So really the only requirement is that it has to be a map. All of the domain elements need to get mapped somewhere, and they only can be mapped to one place, not to multiple places. Okay, so that's what makes a function. All right. So here are some examples of functions. Suppose we form a set D, D for domain, consisting of the people in this math class, and then another set R containing all their heights, right? R for range. So the domain is all of the people in the class, and the range is the heights, right? Now, because every person has one and only one height, we can define a function f by assigning to each person the number corresponding to his or her height. Then D would be the domain of f and R would be the range. Okay, so in this scenario, what would f of Nick equal 74 mean? Well, f is the function that maps people to their heights. So if we have f of Nick equals 74, then that means Nick's height is 74 inches, right? 74 inches. So this means that Nick is 74 inches tall. Okay. Part B says, use function notation to indicate that Marissa is 65 inches tall. Well, if Marissa is 65 inches tall, then we want to map Marissa to 65. So we need f of Marissa to be 65. So we would just say f of Marissa equals 65. Okay? Now part C asks an interesting question. Why can't we define a function the other way around, with D being the heights and R being the people, right? So with the domain being the heights and R being the people. So why couldn't we make a function going that way? Well, the answer is because you could have multiple people with the same height, right? Maybe Marissa is 65 inches and maybe Allison is also 65 inches, right? These are made up people, by the way. But maybe Marissa is 65 inches and Allison is also 65 inches. So you can have f of Marissa equals 65 and f of Allison equals 65. That's not a problem. But what if you wanted to go the other way around and map the height to the person, right? So if we called that function g, right? So if we said, what's g of 65? Well, then it would be ambiguous, right? G of 65 could be Marissa, or G of 65 could be Allison. And because of that ambiguity, we have a problem, right? Because 65 would have to get mapped to two different places, G would no longer be a function, right? So how do we summarize all of that to answer this question? Well, we could say, suppose G, lowercase g, maps heights to people. And suppose that two people, say Marissa and Allison, have the same height. Say 65 inches. Then what's G of 65? Is it Allison or Marissa? Right? We don't know. So instead of IDK, we could maybe say WDK. We don't know. Right? And that's a problem. So that's why we can't define a function the other way around. Okay? Now, that's not always true. There are lots of functions that you could switch the domains and ranges and still get a function. Okay? In fact, those are called one-to-one functions, which we've kind of talked about in the past. We've talked about one-to-one correspondences. Okay. Next example. It says the nucleus of an atom of each element has a unique number of protons known as the atomic number of the element. For example, hydrogen atoms always have one proton, and no other element can have one proton. Oxygen atoms always have 8 protons, and no other element has 8 protons. Okay, so the number of protons is unique to the element. Okay, however, the number of neutrons in a nucleus can change. For example, carbon usually has 6 protons and 6 neutrons in its nucleus, but some carbon atoms have 6 protons and 8 neutrons. These are referred to as carbon-14 isotopes. Okay, and they're using radiometric or radioactive dating. Okay. In fact, each element has at least 2 different isotopes, right? So it's kind of an interesting fact about chemistry. But anyway, so part A says, if we assign each element to the number of protons in the nucleus of an atom of that element, is that a function? So in other words, we're asking if the domain, so if the domain is the set of all elements, right? So the domain would be like the set of all x where x is an element. And by the way, your textbook has a nice picture of the periodic table of elements, so you could look it up. But there's, how many? I think 118 elements, right? So the domain is this, I don't know why I put a colon. I mean, the domain is the set of all x where x is an element. And the range is the set of all, set of all x where x is a number between 1 and 18. Ooh, let me look it up real quick. Let me make sure that that's the number of elements in the periodic table. I feel like that's something I should know, right? Like that's something that we should just know from high school or whatever. Yeah, 118. So 118. So x, where x is 1, 2, 3, all the way up to 118, right? So there's the range. Okay, so if f maps from D to R, is that a function? Well, the answer is yes, because each element has a unique number of protons, right? So yes, because each element has a unique number of protons. So each element would only get mapped to one place. So each input would only get mapped to one output, right? So each input only gets mapped, where do I squeeze this in? Only gets mapped to one output. Okay, so that's good. And then part B says, if we assign each element to the number of neutrons in the nucleus of an atom of that element, is that a function? Okay. So this time the domain is still the same, x, where x is an element. The range, though, it's going to be the number of neutrons, and I don't know how many possible neutrons there are. I suppose anywhere from 1 to 118, but possibly more than that too, because, for example, right, carbon could have more neutrons than protons, so you could have an atom with more than 118 neutrons in it. But anyway, if we assign each element to the number of neutrons in the nucleus of an atom of that element, is that a function? And the answer is no, right? No, because an element could have how should we say this? Could have multiple different numbers of neutrons in its nucleus, right? So no, because an element could have multiple different numbers of neutrons in its nucleus, right? For example, carbon, right? So for example, f of carbon, would f of carbon equal 6, or would it equal 8? Right? So no, this one's not a function because you'd have an input getting mapped to two different outputs, right? So you'd have inputs mapped to multiple outputs, right? So it's not a function. Okay. Moving on. Let me let my dog out real quick. So I'm going to pause this video momentarily. Okay, back. So before we give the next example of functions, we need to introduce a shorthand notation for intervals of real numbers. And this is going to be a notation that we're going to see throughout this chapter. So it's important for us to get a good grasp on what interval notation is. So we're used to seeing set builder notation, okay? But we're gonna use a different notation, and these things are equivalent, okay? So so this first one is the set of all real numbers, right? So the set of all x, where x is a real number, where x is between a and b, right? So the picture, you can draw a number line. You can visualize this on a number line. If a is there and b is there, let me use a different color. So then the set in question would be all of these numbers between a and b, not including a and b. So we leave those as open circles on the endpoints to indicate that a and b are not included in the set, right? In interval notation, we show that a and b, we show all of the numbers between a and b by just writing them inside of a set of parentheses. And we use parentheses to indicate that a and b are not members of the set. Okay. Contrast that with the next one, the set of all real numbers between a and b, including a and b, right? So that's what these lines mean, that x could be bigger than or equal to a, or x could be less than or equal to b. So the picture would look like this. Right, this time we use filled in circles to indicate that a and b are elements of the set. Okay. In the interval notation, we make that change by just changing the parentheses to brackets, right? So the brackets indicate that a and b are in the set. Okay. So and then you can have all kinds of combinations of these things. So you could have where a is not included but b is included. So a is not included, so it gets an open circle. B is included, so it gets a closed circle. That's what that interval looks like. And here's what it looks like in interval notation, right? So a is not included, so we use a parenthesis. B is included, so we use a bracket. You could have it the other way around, where a is included, but b isn't. Right? So a is included this time, but b is not. Okay, and that's what the interval would look like. So hopefully you're kind of catching on to what to how interval notation works. If you're not trapped between two numbers, but x is just allowed to be bigger than something, right? Like here we have all the real numbers that are bigger than some number a. So we would indicate that on the number line by just saying, okay, so it's the set of all numbers bigger than a, but not including a, right? So it's this set. So we just indicate that with an arrow. In the interval notation, we indicate that with an infinity. Okay? We're saying that this is going to go on and on forever in the positive infinity direction. If we want a to be included, then the picture would just use a closed circle. And the interval notation would use a bracket. The infinity always gets a parenthesis, though. Okay? Now, similarly, we could have a situation where x has to be smaller than some number. So if x is less than b, then that would look like this. And we indicate that in interval notation this way, right? So we say, so you'll notice that in the interval notation, the smaller number is always on the left and the larger number is always on the right. in this case, there is no smallest number, right? So it just goes on and on forever in the negative infinity direction, right? So we put negative infinity b. And then since we're not including b, we use a parenthesis, right? If we wanted to include b, then we would use the closed circle in the graph, on the number line, and we would use a bracket in the interval notation. And then finally, if you want to just indicate all real numbers, so if this is your number line, then all real numbers is like, it's just the whole number line. So you just do that with arrows on both ends. And in interval notation, we would write that negative infinity to positive infinity. All right, so that's how interval notation works. A couple things to point out about this is, so when using interval notation, we do not put braces around the intervals. So we don't write this interval as the set A, B, because this is not the same thing as that, right? This would be the set made up of a set, right? So in interval notation, it's already taken for granted that what you're looking at here is a set. So you don't put curly braces around it, right? So don't do that. Another thing that I want to point out, because this is sometimes tricky for students, but the interval from 1 to 3, including 1 and 3, is not the same thing as the set 1, 2, 3. Okay? Because this interval is supposed to be a subset of the real numbers, not just a subset of the integers, right? So you could have non-whole numbers inside of this set. For example, 5/4. 5/4 is 1 and 1/4, right? So 5/4 would be inside of this set, okay? And square root of 3 is also inside of this set, right? Square root of 3 is like 1.7 something, so it's also inside of this set, okay? So the interval from 1 to 3 is not the same thing as the set 1, 2, 3. It would have all of the real numbers in it between 1 and 3. Okay, of course it is true that the set 1, 2, 3 is a subset of the interval from 1 to 3, but there are lots of numbers in this set that are not in this set. Okay, so they're not the same set. In fact, there are infinitely many numbers in this set, which is why we can't really write all of them down, right? So we write it this way, but there are infinitely many numbers between 1 and 3. Another thing, right? The difference between the set 1, 3 with brackets on both ends and 1, 3 with a bracket on one end but the parenthesis on the other is subtle. The only difference between these two sets is that in this set, 1 is included, so 1 is in this set. In this set, 1 is not included, so 1 is not in this set. Otherwise, they're the same set. And then finally, I mentioned this a second ago, but when writing a set in interval notation, the order is very important. The smaller number always goes on the left, right? The larger number always goes on the right. So the interval from -1 to 5, right? That's the set of all real numbers that are between -1 and 5, not including the -1, okay? The interval 5, -1 is just complete nonsense. It doesn't make any sense at all, right? So you always put the smaller number on the left. It's helpful to think of the picture, right? If you notice, the interval notation goes along with the picture very nicely, right? You're always thinking of it from left to right, smallest to largest. Okay, so that's interval notation. Now, all of that for just a little tiny detail in an example that's going to come up pretty soon, but it'll come up again throughout this section, or throughout this chapter. And so I just wanted to give you a thorough understanding of interval notation. But anyway, moving on to our next example now. It says the distance d that you travel while on a walk is a function of the amount of time t that you've been on the walk. If your walking speed is 3.4 miles per hour, which is a pretty quick walking speed, I'd say. I mean, that's kind of a slow jog, but it would be a quick walk. Well, that would be a very slow jog. Oh, so maybe that's like an average walk. I don't know. Anyway, but if your walking speed is 3.4 miles per hour, oh yeah, that's not terribly fast, I guess. That's like an average speed, so never mind. But if your walking speed is 3.4 miles per hour, then for t equals 1 hour, d equals 3.4 miles, right? Of course, right? Because if you go 3.4 miles in 1 hour, per hour, right? Then in 1 hour, you've gone 3.4 miles. All right. So part A asks, what is d when t equals 2? So what is your distance when you've been walking for 2 hours? If you're walking at a rate of 3.4 miles per hour, well, how would we figure that out? Well, we would say you're going to go 3.4 miles per hour, but if you're going to walk for 2 hours, then that means you're going to go 3.4 times 2, right? So we would say d equals 3.4 times 2, which comes out to 6.8 miles. Okay. And then part B says, write an algebraic rule for the function that relates d and t to each other. So we want to write like a formula, I guess, for the distance that you would walk if you travel for t hours. Well, obviously, if you travel for 2 hours, we said it's 3.4 times 2. If you traveled for 3 hours, it would be 3.4 times 3. If you traveled for 10 hours, it would be 3.4 times 10. So in general, if you're going to travel for t hours, then it would just be 3.4 times t. So we would write that in algebraic notation, in function notation, we would say d of t equals 3.4 times t. Okay? So this notation here, d of t, we read this d of t, it doesn't mean d times t, right? So we're not multiplying d times t. We're just saying d is a function of t, right? The distance that you travel is a function of the time that you travel, okay? So distance as a function of time is 3.4 times the time, right? Okay. Part C says, what would it mean for the domain of the function in part B to be the interval from 0 to 3? So the domain, right? The domain, the set of inputs. Well, the output here is a distance, right? It's the distance that you travel. The input is time, okay? The input is time, so how long you travel. The domain is the set of inputs, so these must be times, right? So for the domain to be the interval from 0 to 3, what we're saying is that the times that we will consider for this example are any times between 0 and 3 hours, right? That's what it would mean for the function, or for the domain of the function to be the interval from 0 to 3. So we would say, the function d of t equals 3.4t will model your walking distance as long as you walk for some amount of time between 0 hours and 3 hours, right? So maybe after 3 hours you start to get tired, right? And so your pace slows down and you're not walking at 3.4 miles per hour anymore, right? So this function is only good if t is between 0 and 3. So in other words, i.e., the function is only good if t is between 0 and 3 hours. Okay, so that's what it would mean for the domain of the function to be the interval 0 to 3. Okay, part D. If the domain of the function in part B is d equals 0, 3, what is the range, r? And let's use interval notation to write it down. So what would the range be? So remember, the range is the set of outputs. So if our set of possible inputs is 0 to 3, what's the set of possible outputs? Well, we could see, we could see what the possible outputs are, right? When our input is 0, the output is 0. When the input is 3, The output is, what would that be? So 12, carry the 1, 9, 10. So I think 10.2. Oh goodness, why was that so difficult? That shouldn't have been so difficult to come up with, but yeah. Yeah, 10.2. Okay, so and then it stands to reason that like you're never going to get anything, you're never going to get an output smaller than 0, because as long as you're walking for some amount of time, you're going to go some distance, right? So the distance is never going to be smaller than 0. And the distance is never going to be larger than 10.2 because you're only going to walk for up to 3 hours, right? So you're not going to walk longer than 3 hours. And so if you walk, and if you do walk for 3 hours, then you go 10.2 miles. So you're never going to, so you're not going to walk further than that if your time is limited inside of that interval. So the domain is 0 to 3. That means the range would be from 0 to 10, right? So the range would be 0 to 10.2. Okay? Right, so the set of outputs would be anything between 0 and 10.2. Okay. So I think I mentioned this word on page 1 when we first talked about the definition of functions, but the word image is used by mathematicians when speaking of a specific member of the range. In the previous example, the image of 2 hours is 6.8 miles. Right? In example 1, the image of Marissa is 65 inches. In other words, it's a particular output, right? So image is synonymous with output, right? So we say image equals output. Okay? But in mathematics, really, we use the word image more than we use the word output. Anyway, for any function f, we think of f of x as the image of x after applying the rule f to it. Okay? If that's confusing language, try not to be too confused. It's really pretty straightforward. The image is just the output, right? So if you have a particular domain element, then the place that the domain element gets mapped to is called the image of that input, right? So the image of 2 hours, right? If the input's 2 hours, then its output, its image, is 6.8 miles. Okay? If the image is Marissa, like in example 1, then the output is the image, right? In other words, the output is 65 inches. Okay. So that's what we mean by image. I'm just introducing that vocabulary because you're going to see that vocabulary used in the homework, and I wanted you to know what it meant, right? So let me give you some examples. Philip has accepted a salesman's position at a computer store and is offered a choice of compensation, either $400 per week plus 12% commission on his sales, or $450 per week plus 10% commission on his sales. So you can get $400 a week plus 12% commission, or $450 per week plus 10% commission. In order to reach a decision, right, Philip asks himself 2 questions. He wants to get the best deal for himself, right? So in order to figure out what the best deal is, I mean, that depends on how much he's going to sell, doesn't it? Because if he sells a lot, then going with the smaller weekly amount but getting a larger commission might be good. If he doesn't think he's going to sell very much, though, he probably wants more per week and a smaller commission. So in order to reach a decision, Philip asks himself 2 questions. For what dollar amount of sales will these options yield the same payment? So, in other words, how much would he have to sell in order for him to make the same amount of money, whether he went with this option or this option? Well, in order to answer that question, I think the first thing we would want to do is come up with an expression for how much he's going to make using each option, right? So I'll call this first option option 1, right? Option 1. Right? How much is he going to make for option 1? He's going to earn $400 regardless of how much he sells. but then he's also going to earn a 12% commission on how much he sells. So let's say that he sells X dollars worth of stuff, right? So he sells X dollars worth of stuff. Then his commission is going to be 12% of X, right? So 12% of X, you would rewrite that as 0.12 times X, right? So that's how much commission he makes, but then he also gets his weekly just flat rate of $400. So it would be, so the total amount of money he would make in option 1 would be 0.12 times X plus 400, right? Okay. For option 2, the amount of money that he makes is going to be following a similar line of reasoning. If we say he sells X dollars, then the commission he's going to make is going to be 10% of X, right? So 0.10 times X. But then the total amount of money he's going to make is going to be his commission plus that weekly rate of 450. So it'll be 0.10 times X plus 450. Okay. Now what we're being asked is, when will these things be the same? When will this equal that? So for what dollar amount X will these two things be the same? So let's see if we can figure that out. In order to do that, we're just going to set these two expressions equal to each other, and we're going to solve for X. So some of you might be a little bit rusty on your algebra skills. That's okay. Let's walk through it together. Okay, so the idea is that you want to get all of your x's together on the same side of the equal sign, and then you want to get all of your non-x's together on the other side of the equal sign. Now, it doesn't matter if you start by moving the x's around or if you start by moving the non-x's around, and it doesn't matter which side of the equal sign you decide to get stuff on, right? Whatever you do, it's just sort of up to you. So as long as you end up with your x's on one side and your numbers on the other. So I want to get this term and this term together. And the way that I do that is I perform the opposite of the operation that I see. So actually, I think I'm going to start with the numbers just to make it more clear for those of you who are a little bit rusty on this. So I'm going to start by getting this 400 and this 450 together. Now currently I'm adding 400. I'm going to try to move this 400 over to this side. Okay. Currently I'm adding the 400, so in order to get rid of it, in order to cancel it off, I need to subtract a 400. Now, I'm allowed to do that as long as I also subtract a 400 from this side. And the reasoning is, you can think of this like a balance scale. So if you've got a balance scale, oh, I'm going to do a horrible job of like drawing this, but you've got a balance scale, right? If you've got like a bunch of items over here, and they're in balance with a bunch of items over here, if you take one of these things off, it's going to get out of balance, right? But if you take the same amount off on the other side, it's going to come back into balance. Ooh, you can't see what I was drawing. Shoot. Well, anyway, let me draw it again. So you've got your balance scale, right? You've got some number of items in balance with some number of items, right, on the other side. If they're in balance, once you take one of these things off, it's going to get out of balance, right? This thing is going to go up and this side's going to go down. But if you take off the same amount on the other side, it's going to come back into balance, right? So the idea is I can subtract 400 from the left side of the equation as long as I subtract 400 from the right side of the equation as well. And if I do that, then I'm left with 400 minus 400 goes to 0, right? So this is just 0.12x. On the right-hand side, I'm going to have the 0.10x. And 450 minus 400 is 50. So I'll say plus 50. Okay, so now that I've chosen to get my numbers on the right-hand side, I need to force my variables to get on the left-hand side. And so the way I'm going to do that is I'm going to move this 0.10x over to the other side. And again, I'm going to do that by subtracting it, right? I want to get rid of it, so I'm going to subtract it. Okay. And when you subtract 0.12x minus 0.10x, you don't have to worry about the x's. Just subtract the numbers, right? 0.12 minus 0.10 is 0.02. And then just bring the x along for the ride. On the right-hand side, these things will just cancel and leave me with 50. And then last but not least, I want to get x by itself, right? I want to figure out what x itself is. So if I think about, well, what's going on here? It's multiplication, right? I've got 0.02 times x. Well, in order to undo multiplication, I need to do the opposite of multiplication, which is division. So I need to divide by 0.02. And then just use your calculator to figure out what this is. So 50 divided by 0.02. Just punch that into your calculator. You should get 2,500. So here 0.02 times something divided by 0.02. Those are just going to cancel. I'm going to get x equals 2,500. Okay. And so that's the answer to the question, right? For what dollar amount will the sales of these options yield the same payment? $2,500, right? So if Philip sells $2,500 worth of merchandise, then he'll make the same amount in option 1 as he does in option 2. You can verify this, by the way. So we're saying 2,500. Let's make sure that they're the same. If I plug in 2,500 here, 0.12 times 2,500 plus 400, I get 700. So that's how much money he makes, $700. If I plug it in here, 0.10 times 2,500 plus 450 is also 700, right? So he makes the same amount if he sells this much. Merchandise. If he sells more than this amount, like if he sells $3,000 worth of merchandise, he's going to make more in option 1, right? Because he gets a higher commission there. And I won't bore you with the details, but you can try that out. Plug in 3,000 to each of these. You'll see that this one's higher. Okay. So this is sort of his break-even point, you might say. Okay. All right. Part B says write a function for each compensation option. We've already kind of done that. If Philip feels he will consistently sell $3,500 of computer equipment per week, which option will pay him the most money? All right, so we've already kind of done this, right? Option 1, we'll call it f of x equals 0.12x plus 400. Option 2, let's call it g of x equals 0.10x plus 450. Okay? So now we want to know if he sells $3,500, which option will pay him the most? Well, I've kind of already given away. It's going to be option 1. But the way you would see that is by plugging in 3,500 to each of these, right? So we can say f of 3,500 equals 0.12 times 3,500 plus 400, which you can plug into your calculator, right? So 0.12 times 3,500 plus 400 is 820. Okay. G, so option 2 of 3,500, 0.10 times 3,500 plus 450. That's $800. Okay, so in option 1, he's going to make $820. For option 2, he's only going to make $800. So which option pays him the most money? It's option 1, right? Right? But again, this is assuming that he sells this much merchandise. as long as he sells at least $2,500 worth of merchandise, he's going to make more in option 1. But if he sells less than that, if he only sells $1,000 in merchandise, he'd be better off going with option 2, right? Anyway. Okay, so note that in the previous example, the answer to part A, in the previous example, to answer part A, the unknown quantity represented a specific number that we could deduce from the given information, right? X represented the break-even point, right? So it was X represented one specific number, okay? On the other hand, in part B, the unknown quantity could represent any of a variety of different quantities, right? We could plug in any number we want to this function. So X represents a whole bunch of different numbers in part B. So this is kind of confusing to students, I think, at first. But for that reason, I'm going to make a distinction, right? So whenever you have a letter that represents some unknown quantity, but it's a fixed unknown quantity, I'm just going to call it an unknown. Okay? I'm just going to call it an unknown. But whenever you have a letter that represents some unknown quantity that changes, I'm going to call that a variable, right? Because it can take on a variety of different quantities, right? It can vary, so we call it a variable. Now, 2 variables were needed to form each relationship in part B, right? So whereas in part A we just had one unknown, in part B we had 2 variables, right? We had the input variable and then the output variable. So 2 variables were needed to form each relationship in part B, indicating that as one variable changed, the other variable had to change accordingly, right? When our inputs in part B changed, our outputs changed, right? So if you change your input from 3,500 to like 2,500, your output's also going to change from 820 to 700, I think is what it was. Anyway, we call the variable that's allowed to change freely the independent variable, and the one that has to change in a particular way in order to conform to the change in the independent variable, the dependent variable. So the independent variable is the one that you change around. It's your input, right? It's your input. The dependent variable is the output. So you could kind of think of it that way too. So you can say the independent variable is your input. The dependent variable is your output. Okay? So in part B, the independent variable was, well, what were we plugging in? We were plugging in the amount of money that he would sell. Right? So the independent variable is the amount sold. The dependent variable is the output, right? That's how much money he made, right? That's how much money he made. So amount made, or amount Philip is paid. So maybe just to make it clear, we can say amount, the independent variable, the input variable is the amount Philip sells, right? And the dependent variable is the amount Philip is paid. Okay? So that's that. We still haven't used the word image yet, right? But I think we'll see an example of the use of the word image. Okay. So couple more examples, but first let's talk about this idea. So a function is called increasing if f of x in the range always increases whenever x in the domain increases. On the other hand, if f of x decreases whenever x increases, then we call f a decreasing function. So for example, the older a child gets, the taller she gets. So the function that maps her age to her height would be an increasing function, right? As she gets older, she gets taller, so it's increasing. On the other hand, the higher a mountain climber climbs, the lower the air density. So the function that maps altitude to air density is a decreasing function. The higher you climb, the lower the air density. Okay? Now, not all functions are increasing or decreasing. They could be monotone functions, so they might not change at all, or they could increase on part of their domain and then decrease on another part of the domain. But still, this is a useful way to kind of classify functions as increasing or decreasing or neither. So let me give you some more examples, right? So example 5 says the circumference c of any circle is related to its radius by c equals 2 pi r, where pi is about 3.14, right? So 2 times pi times radius r. That's the circumference of the circle. The circumference is the distance around the circle. So maybe I should point out, right? This would be the circumference. The radius is the distance from the center of the circle to the edge of the circle. So that's the radius r. So the circumference is 2 times pi times the radius. Okay. Part A asks, what is the circumference of a circle with radius 3 feet? Right, so the circumference of a circle with radius 3 feet is going to be 2 times pi times 3. Okay, that's 6 pi, or if you just punch it into your calculator, 6 pi is approximately 18.8. Right, 6 pi is approximately 18.8 feet. Part B asks, is this function increasing, decreasing, or neither? Well, in order to be increasing, we would need for the output to increase whenever the input increases. So imagine if instead of 3, you put in 4. Would the output get bigger or smaller or stay the same? Right? And the answer is it would get bigger, obviously, right? If you plug in 4 instead of 3, this is going to go from 6 pi to 8 pi. 8 times pi is going to be bigger than 6 times pi, of course, right? So if your input increases, your output also increases. So this is an increasing function. Right? If we increase the input, the output also increases. Okay? All right. Here's another example. It says the rate at which a mammal's heart beats is approximately a decreasing function of the size of the mammal. Right? So in other words, the bigger you are, right? The bigger your size, the lower your heart rate. Okay? Given this information, who has the faster heart rate? An elephant or a mouse? An elephant or a mouse? Okay. Well, the elephant's bigger than the mouse, right? So the elephant's going to have a slower heart rate than the mouse. So who has a faster heart rate? I guess the mouse, right? We would say the mouse has a faster heart rate. Okay, and I'm just going to say, note, this is a decreasing function. Because as size increases, heart rate decreases. Right? So as your size increases, that's your input, the heart rate, which is your output, decreases. Okay? So as your input increases, your output decreases. That means that the function is a decreasing function. Anyway, but the answer to the question we were asked is the mouse, right? The mouse has a faster heart rate. Okay, one more example. So this one says the study of integers and their related properties is called number theory. It's a branch of mathematics called number theory. Any function whose domain is the set of integers is called a number theoretic function. You don't really need to know that except for like on the homework, right? You might see some problem that says, oh, look at this number theoretic function. And I don't want you to freak out, right? This is what it means, okay? So it's any function whose domain is the set of integers. Okay. One such function is denoted by the Greek letter tau. Looks like a little T, but it's the Greek letter tau. And the tau function defines tau of n to be the number of positive divisors of n. So for example, tau of 10 would be 4, because 10 has 4 divisors. The divisors of 10 are 1, 2, 5, and 10, right? So a divisor of a number is, a divisor of a whole number is another whole number that divides that number evenly, right? So 10 divided by 1, 1 goes in evenly, it goes in 10 times. 2 goes in evenly, it goes in 5 times, right? 5 goes in evenly, it goes in twice, and 10 goes in evenly, it goes in once, right? So those, and no other number goes in evenly, right? Like 4 doesn't go into 10 evenly. 4 would go into 10 2.5 times, right? So 4 is not a divisor of 10 because it doesn't go into 10 an even, or sorry, it doesn't go into 10 a whole number of times, okay? Anyway, so these are the only 4 divisors of 10, and so tau of 10 equals 4, right? Similarly, tau of 30 equals 8, because 30 has 8 divisors. The divisors of 30 are 1, 2, 3, 5, 6, 10, 15, and 30. And you can verify that, right? 1 goes into 30 30 times. 2 goes into 30 15 times. 3 goes into 30 10 times. 5 goes into 30 6 times. 6 goes in 5 times. 10 goes in 3 times. 15 goes in twice, and 30 goes in once. But there are no other divisors of 30, and so tau of 30 equals 8. Okay, so with that in mind, now let's calculate tau of 4, tau of 6, and tau of 9. Okay, so in order to do that, we need to figure out what are the divisors of each of these numbers. So divisors of 4, well, 1 goes into 4 an even, or a whole number of times, right? It goes in 4 times. 2 goes into 4. 3 doesn't go into 4, but 4 goes into itself. Okay, so the divisors of 4 are 1, 2, and 4. Therefore, tau of 4 equals 3, right? Because there are 3 divisors of 4. Divisors of 6. 1 goes into 6. 2 goes into 6 3 times. 3 goes into 6 twice. And then 4 doesn't go into 6. 5 doesn't go into 6. But 6 goes into 6. So tau of 6 equals 4. Right? Because there are 1, 2, 3, 4 divisors of 6. Okay? See if you can do 9. Give the video a pause and see if you can figure out tau of 9. Okay, here's my solution. So divisors of 9. 1 goes into 9. 2 does not go into 9. 3 goes into 9, right? 3 goes in 3 times. 4 doesn't go in. 5 doesn't go in. 6 doesn't go in. 7 doesn't go in. 8 doesn't go in, but 9 does. Okay? So tau of 9 equals 3. Right? There are 3 divisors of 9. 1, 2, 3. So tau of 9 equals 3. Okay, so then part B asks, is tau increasing, decreasing, or neither? Well, let's see. Here we increased the input from 4 to 6, and the output also increased from 3 to 4. But notice that when we increased the input again from 6 to 9, the output decreased again from 4 back down to 3. So it increased from here to here, but then it decreased from here to here. And so that means this function is neither. It's not increasing, it's neither increasing nor decreasing, right? Between some numbers it'll increase, and between other numbers it'll decrease. So it's, we can't say that it's always increasing or always decreasing, right? So it's neither. Okay, neither. Okay. And then final note says, note that tau assigns the same image to more than one domain element, but tau is still a function since each domain element only has one image, right? Right? Yep, so each input has only one output. However, you do have multiple inputs going to the same output. That's okay though, right? You just can't have one input going to multiple outputs. Okay, so that's all. That's all I want to say about functions, or at least an introduction to functions.